Welcome to A3, Work, Energy, and Power, Part 3, where we will look at mechanical energy. Looking at the standards guide, we see that mechanical energy is the sum of kinetic energy, gravitational, and elastic. We also see that this energy will be conserved. The law of mechanical energy says that mechanical energy will be conserved in a closed system. And also we're told that we're going to be working with a couple of a few formula. These are the ones that I highlighted that should come up in this video. The formula that are provided for you, also here highlighted, is the formula for kinetic energy. That is this one right here. 1/2 mv squared is the amount of energy that comes from motion. And then the energy that comes from a gravitational field, the gravitational potential energy, is mass times gravity times your height. The next one that we see refers to the elastic energy of a spring, but I don't think that comes up in this video. Also, some of the kinematics formula, I think this will come up, or we'll use it to compare techniques for solving a problem. But now let's just get started with the basic definitions. So mechanical energy consists of a few components. We have kinetic energy, which is 1/2 mv squared that we mentioned in the formula guide, and we'll be using that today. And also gravitational energy, which is mass times gravity times height. And that is the energy that is provided by, or that's given to an object due to its position within a gravitational field. So the higher up an object is, the more potential energy it has in a gravitational field because it could fall, acquiring more and more kinetic energy. We'll be using this idea to solve the main problem of this video. And we also have elastic potential energy, which comes from energy stored in springs or any other object or any other mechanism that could stretch or compress in a similar manner to a spring. Conservation of energy, we mentioned it earlier, but it's going to be important for solving these problems, that within a closed system, absent any sort of friction or resistive force, the mechanical energy will remain a constant. Therefore, might change. In other words, we're going to see that there might be more kinetic energy or less kinetic energy, but if there's any change there in kinetic energy, it has to be compensated with one of the other forms because the overall mechanical energy has to remain a constant. This is known as the conservation of mechanical energy. And we will see that here with the first problem where they want us to use the law of conservation of energy to solve the problem, to find out what will be the speed of a stone prior to hitting the ground. So in this case here, we have a 50 meter cliff. A person, Alex, takes a stone and he drops it down at 5 meters per second. And we are tasked with finding out what is going to be the speed of the stone immediately prior, question marks, what will be its velocity immediately prior to making contact with the ground. And we want to solve this using the law of conservation of energy, the conservation of mechanical energy. And we could go about doing this by, one, figuring out the amount of energy that the system is starting with. This will consist of both kinetic and gravitational. Once we find out that total, we could also solve for velocity at the final stage right before it makes contact. Because what's going to happen right before it makes contact, we will only have kinetic energy. There'll be no more potential energy. It would have already reached point zero. Let's start writing out the numbers to make this a little bit more clear. So this stone will have both kinetic and gravitational potential. Its kinetic energy, which comes from that 5 meters per second squared, kinetic energy, which is 1/2 mv squared, is going to equal 1/2 the mass of the stone, 0.5 kilograms, times the velocity, 5 meters per second squared, and that is equal to, let me plug it in here, we get back 0.5 times 0.5 times 5 squared, which is 25, and we get back 6.25 joules. which comes from the kinetic energy. But that's not the only energy we have. We also have gravitational potential energy, which comes from potential energy, which comes from its position, its height. Right, so this is mass times gravity times height. So we have the same mass, which is 0.5 kilograms. We have the height, we have gravity, which is 9.8 meters per second. And we have the height, which is 50 meters. We plug this in, and we end up getting back 0.5 times 9.8, 0.5 times 9.8 times 50 gives you back, in this case, let me do it again. It is, did I type this out right? No. One more time. 0.5 times 9.8 times 50 comes out to 245 joules. And in total initial energy will be equal to 245 plus 6.25, which is equal to 251.25 joules. Or I'll round this to 252. Let's just round it to 252 joules. Right, so now, given that information, how can we figure out what will be the velocity right before the stone hits the ground? Well, let's do 252. That amount of energy has to still be there at that final stage. The energy shouldn't change. But what's going to change? The formation of the form of the energy. We're right before the stone hits the ground, we won't have any more potential energy. We won't have any more gravitational potential because its height will be 0. In other words, we won't have any more energy coming from gravity. All of the energy must come from kinetic energy. So 252 joules needs to equal 1/2 mv squared, where the mass is still 0.5. That didn't change, 0.5 kilograms. And we solve for v. So I could divide, let's see, I'll just divide 252 divided by 0.5 gives me 504 equals v squared, which means that by itself we are at, right, so that means that by itself, let's go and put this, it was 252 divided by, not by 0.5, by, excuse me, it's 252 divided by 0.25. So it should be 252 divided by 0.25, right? 0.5 times 1/2 gives me 1008. There we go. So that made more sense. We get 1008 joules equals v squared. The velocity by itself is equal to the square root of that, which is equal to 32 meters per second. So based on the law of conservation of energy, we figured out what the initial total energy was, which was 252 joules. And then we said that the final stage, the point that we were looking for right before the stone hits the ground, 252 joules must equal the total kinetic energy, 1/2 mv squared. We solved for v, which is 32 meters per second. Part B is the same question, but now it's telling us to solve with our kinematics equations, which is why I put those on in the slides. If we go up to our kinematics equations from A1, nice little review, and also just to show that physics should work no matter how we solve it. If we use a correct method, we should get the same answer, obviously. And now I'm going to use the kinematics equations to solve this problem, given the information that we have. So let me just write out v squared. So v squared, which is that final velocity that we're looking for, is equal to the initial velocity plus 2 times acceleration times distance. S is distance in our kinematics formula. let's plug in. The initial velocity u was equal to 5, so we have 5 squared plus 2. Acceleration is 9.8 meters per second. Distance is 50 meters. And we plug in these numbers. Let's see, I get back 5 squared is 25 plus 2 times 9.8 times 50. And I get here, right, so I get here essentially the same thing depending on how we round. So this came out to 1,005. And V by itself is equal to 32 meters per second. The same answer that we had above. But here we solved it with our A1 kinematics material. In part A, we solved it by using the law of conservation of energy. In both cases, we came out to the same answer of 32 meters per second. A little bit of a difference here due to only due to rounding. Right here, I have 1,008 joules, but don't let that throw you. The only difference was due to rounding, and our final answer came out to be the same, 32 meters per second. Right, so a nice problem. We solved it two different ways to illustrate both the law of conservation of mechanical energy, how energy could change forms from kinetic to gravitational within a closed system, but the overall energy should be constant. And then in part B, we had a little review of our kinematics formulas in order to show that we get to the same answer, that either way that we do it, our physics holds true. And that brings us to the conclusion of part 3. I look forward to seeing everybody for part 4, where we'll make some more progress with our with work, energy, and power. See you all there.